It's awake again. After slipping quietly behind the sun, the mysterious interstellar visitor known as 3I Atlas has reemerged, and not without a few surprises. On October 29, 2025, it passed through perihelion, glowing faintly at magnitude 9.5. To most, it was invisible, but to scientists tracking every flicker of light, it was a whisper that something unusual was happening. Subtle, real, non-gravitational movements were detected, tiny accelerations flagged by JPL's A1 and A2 parameters, right as a solar CME blasted through its plasma cocoon. That was enough to make the astronomical community pause. And of course, the big question followed. Is this alien technology at work, or just good old comet physics doing its thing? Before diving into theories that light up online forums, let's start with what's actually been seen so far, the real, measurable data. From where we stand on Earth, 3I Atlas vanished behind the Sun at its closest approach. That alignment meant even the world's most powerful telescopes were temporarily blinded, forced to sit in silence as the comet hid in solar glare. For a few tense days, humanity's watchful eyes couldn't see it at all. But space, as always, had another vantage point. High above the noise, the Punch mission kept watching. By layering image after image taken in late October, Punch scientists managed to extract a faint glimmer. 3I Atlas, holding steady, still alive, still there, shining weakly at magnitude 9.5. That's far below what the naked eye could ever perceive, barely scraping the limits of mid-range amateur telescopes even under perfect skies. Unlike Earth-based observatories, spacecraft don't have to fight through the sun's blinding brilliance or Earth's atmosphere. They can peer closer, right up to the sun's edge, where most objects simply vanish into daylight. Still, even then, the comet appeared as a soft blur against a sea of solar light. No majestic tail, no flashy jets, just a calm, glowing smudge, quietly surviving the chaos near the sun. As October faded into November, the geometry began to change. The comet started inching away from the sun's glare, its elongation angle widening bit by bit. That slow drift is a sign of return. 3I Atlas was coming back into view. Now astronomers around the globe, professionals and backyard enthusiasts alike, are holding their breath, scanning the dawn sky for its next appearance. For now, every new frame comes with uncertainty. The brightness is only roughly estimated. The coma remains unresolved. And if there is a tail, it's little more than a whisper. Yet what matters is this. Even after vanishing behind the sun, 3I Atlas never disappeared. Each morning brings sharper data, clearer signals, and a more defined sense of where this interstellar wanderer truly is. Then comes the puzzle. Its orbit doesn't perfectly match the predictions. Subtle mismatches, just a few arc-seconds off in right ascension, hint at something pushing it ever so slightly off course. It sounds dramatic, but in truth, it's a familiar story to comet scientists. These delicate deviations are explained by non-gravitational forces, tiny jets of gas bursting from the comet's surface as sunlight warms it. To describe those nudges, astronomers use two trusted parameters, A1 and A2. A1 measures the acceleration along the line between the Sun and the comet, while A2 captures the sideways drift across its orbit. For 3I Atlas, JPL's current models list A1 at about 1.7 times 10 to the negative 6th astronomical units per day squared, and A2 near 7 times 10 to the negative 7th astronomical units per day squared, perfectly normal for a moderately active comet. Those numbers may look tiny, but in the precise world of astrometry, they speak volumes. When scientists feed data from ALMA and other observatories into their orbital models, using the Marsden formalism, the gold standard for such fits, everything begins to align. The observed and predicted paths fall neatly within expected noise levels, usually within a single standard deviation. In other words, 3IATLS isn't breaking the rules of physics, it's just playing them beautifully. Another visitor from beyond, whispering stories of the deep interstellar dark, one faint arcsecond at a time. A quiet voice from NASA's Jet Propulsion Laboratory summed it up best. We're not seeing a spaceship, we're seeing physics, just cometary physics cranked up by a stormy sun. In other words, nothing alien, nothing artificial, just the universe doing what it does best, surprising us with its natural extremes. The small accelerations measured on 3IATLS aren't the signatures of engines or intelligent design. They're exactly what scientists expect from a comet, a small icy core venting gas as it heats up and races through the inner solar system. To experts, this is business as usual, but to everyone else, it feels like watching nature rewrite its own limits. The real fascination, though, isn't about proving what it isn't. It's about understanding what's truly happening around this interstellar traveler, because the conditions it's facing are wild. And to make sense of it, we have to talk about something that sounds like science fiction, but isn't. Plasma. Plasma isn't just a fancy physics term, it's the fourth state of matter, the one that fills most of space. Around comets like 3IATLS, plasma is everything. It's the invisible stage where energy, particles, and magnetism perform an electric dance. Scientists break it down into 5 main processes, each shaping the comet's strange and shifting behavior. It begins with photoionization. Sunlight so intense, it knocks electrons off gas molecules spewing from the comet's surface. In an instant, neutral atoms become charged ions. Then comes charge exchange, where high-speed ions from the solar wind collide with those cometary atoms, swapping electrons and creating glowing X-ray emissions that trace the invisible turbulence between them. Next up is mass loading. As these newborn ions flood into the solar wind, they slow it down and build pressure, reshaping the magnetic environment around the comet. Picture a river of charged particles suddenly meeting a wall of resistance. It piles up, ripples, and bends. Then comes the bow shock, a wave that forms at the front of this invisible struggle, much like water curling around the bow of a speeding ship. The solar wind slams into the comet's expanding atmosphere and is forced to yield, abruptly.
Finally, there's the ionosphere, or what scientists sometimes call the cometopause. It's the unseen border where the comet's plasma pushes back hard enough to carve out a protective bubble. Inside it, the comet rules its domain. Outside it, the solar wind rages. And all 5 of these processes are happening right now around 3I Atlas, defining its light, its movement, and its unpredictable flickers in the data. Even the dust around it isn't just drifting silently. Each microscopic grain is charged with tension, literally. Bombarded by high-energy particles and ultraviolet light, the grains slowly build up static charge. When that charge crosses a critical threshold, the grain can't hold together anymore. It explodes. One becomes many. A tiny cloud of fragments scatters into space, each speck lighter, more reactive, and far more sensitive to radiation and magnetic fields. Suddenly, these fragments whip and twist unpredictably, and when that happens en masse, the comet's brightness can spike dramatically, as though it just flickered awake. These micro-explosions aren't rare, they're part of the life of a comet. And when a solar outburst sweeps past, injecting even more energy into the scene, they can happen in bursts. We've seen it before, most famously in July 2015, when the European Space Agency's Rosetta spacecraft was orbiting Comet 67P. That summer, the Sun hurled a coronal mass ejection straight toward the comet.
Within hours, Rosetta's magnetometer went wild. The readings jumped from about 50 nanoteslas to nearly 300 NT, a six-fold surge. One engineer's voice cracked through the mission loop. "It's a magnetic wall." In that moment, the comet's plasma cocoon transformed. The magnetic field didn't just ripple, it snapped, expanding and compressing like a living thing under stress. Rosetta's instruments caught the chaos. Charged particles surged, the plasma boundary ballooned outward, then collapsed back as the solar storm passed. All of it happened in minutes, not days. For scientists, that Rosetta event became a landmark, a vivid reminder that comets aren't fragile snowballs drifting quietly through space. They're armored in magnetic skin, capable of reshaping themselves when the sun gets angry. And this is why the comparison matters. When 3IA-TLS made its recent close pass during a time of heightened solar activity, the same kind of forces likely came into play. The data from Rosetta gives scientists a playbook, a scale to measure just how intense these interactions can become. A CME doesn't just brighten a comet, it can supercharge it, wrapping it in a storm of plasma and magnetic fields that changes everything for hours, sometimes days. So as 3IA-TLS emerges once again from the sun's blinding glare, every faint pulse, every spike in brightness, every tiny shift in its trajectory could be telling a story written not by aliens or engines, but by the raw electric heartbeat of the cosmos itself. November is shaping up to be a cosmic roller coaster for anyone eager to witness 3IA-TLS in motion. As dawn breaks on November 4th, something remarkable happens. Venus, the Sun, and the comet align almost perfectly in space. It's the kind of celestial geometry that tends to light up social media with bold theories and wild headlines. But for astronomers, it's not about speculation, it's about precision. That alignment means the comet hovers just 29 degrees from the Sun, hugging the horizon in the faint blush of pre-dawn. In other words, catching a glimpse won't be easy. Yet every sunrise pulls Atlas a little farther from the sun's glare, each day giving us a few more degrees of breathing room. Then on November 5th, the sky turns theatrical again. A supermoon rises, flooding the heavens with light. For observers, it's both awe-inspiring and frustrating. The moon's brilliance drowns out faint objects like the comet, even as the geometry slowly improves. By November 7th, the sun itself joins the drama. A cluster of large sunspots rotates into view, a sign that the solar surface is restless. More sunspots often mean more flares and possibly another coronal mass ejection, the same kind of solar blast that once shook the plasma cocoon around Comet 67P during the Rosetta mission. Meanwhile, 3IA-TLS climbs to about 36 degrees from the sun, finally lifting higher in the dawn sky. Mid-November brings the real opportunity. Between November 14th and November 17th, the comet's elongation stretches past 50 degrees, clearing the horizon well before sunrise. That's when backyard astronomers with a bit of luck and a 4-inch telescope might finally spot it. Don't expect fireworks. It's still a faint, compact traveler, slowly dimming as it drifts away from the sun, its once vivid activity cooling into silence. Then comes December 19th, a date already circled in red on many astronomers' calendars. That's when 3IA-TLS makes its closest approach to Earth, roughly 1.8 astronomical units away. High above in the constellation Leo, it'll be ideally placed for telescopic viewing, though its light will have faded further, likely around magnitude 12 or even fainter. A quiet visitor far from the spectacle some might hope for. Fast forward to January 9th, 2026, and the night sky stages yet another act, a planetary lineup, featuring Atlas, Jupiter, Mars, and Venus all gracing the same region of space. It's the kind of event that headlines love to exaggerate, a cosmic alignment, a celestial sign. But once again, science keeps us grounded. The comet will still be distant, dim, and demanding patience, a reminder that the universe doesn't perform for clicks.
And maybe that's the lesson in all of this. With so many dates, alignments, and online buzz, it's easy to get lost in the noise. But astronomy rewards patience, not hype. If a post claims naked eye visibility, glowing tails, or, heaven forbid, alien propulsion, take a breath and check the data. Real discoveries live in measurements, not in viral graphics.